Hi, in this talk I will be discussing our recent work on applying constraint programming on symmetric cryptography. So let's start by a bit of context. In symmetric cryptography, we have some people who want to send some message across the internet, but we want this message to be secure. Like no one can read the message until he or she knows the key. So when the message is around the internet, we want it to be secure, and then when it gets to the receiver should also have the key, decipher it, and get the final message. What's very important is to make sure the cipher is actually secure, so no one can read the message until having the key. And we do that by trying to break it. If we succeed to break it, it means that the cipher is not secure and we try to find another one. If we don't succeed to break it, it means that probably it is secure, so we may keep it for a few years. One of the most famous attacks is known as the related differential cryptanalysis. So the idea is to start with a message X. Possibly we can inject some difference called delta X, and we will obtain a new plaintext message. Then each of these messages go through some cipher, and at the end we get some cipher text called Y and some cipher text with a difference delta Y. And what we want to find to attack the cipher is to find some tuple delta Y and delta X, so that the probability of having delta Y given delta X is maximized. And there's two kinds of attacks we can do with that. We can do what we call single key, so we are only allowed to inject differences in the plain text, and we have the related key attack, in which we can also inject differences in the key. So this problem is quite challenging if we want to tackle it at first. So a lot of people try to find good ways to find good probabilities. And one groundbreaking strategy used something very similar to abstract interpretation. So it's a two-step process. In the first step, we are grouping some bits together into a k-bit sequence. So instead of having a lot of bits, we will have some packets. And we just care about if there is a difference or not. So if there's a difference, we will just remember there is a difference. And if there's no difference, we just remember there's no difference. So this is an approximation, a higher view of the problem, which is not necessarily feasible. So we have to solve a second step, which is called the step 2, in which we try to make it concrete, to check if it's concretizable. So this process is great and it works quite well in most cases, but there's still one problem. While the step 2 is quite straightforward to solve because it's very close to the original cipher, the step 1 is quite challenging because we have to make sure that the abstraction we get is efficient, and this requires some complex models. So to design such complex models, many skills are required because we have to be familiar with symmetric cryptography and we have to be also familiar with constraint programming. It takes a lot of time to build such models, and people can expect to spend at least a few months just to come with one model. Such models can also contain bugs and a lot of redundancies from one cipher to another. So one question we may ask as AI researchers is, can we automatize this process? For instance, can we design the cipher into some unified language, push a button, and obtain all the models for free? So in this paper we asked this question, and actually this answer is yes. So we can come with some general procedure that will take as an input some cipher and will produce some mini-zinc models. So the first thing we have to consider when we want to build some generic toolbox, we have to think about the input format. So what we chose in this paper is to consider to modelize a cipher using some DAG. So each node will represent either some parameter, which will be some possible value taken by a variable, and some operator, We can see them as some kind of black box function. So let's take an example. A DAG may look similarly to that. So we have, for instance, some state to represent the key, some state to represent the plain text. Then each of these states goes through some operator. In this case, it's a XOR. It will produce possibly some internal state, then goes through some other operator, for instance, an S box, and at the end we get some ciphertext. This is a very simplistic view, but it gives an overall description of the kind of format we are working on. And here we can see some possible values. So if we give the key 2 and the plain text 3, it goes through the XOR, it produces some value 1, and then if it goes through some S box, let's say it produces the value 6. Okay, so now that we have our unified modeling language, we can now perform what we call some shaving. So the idea of shaving is to apply successively some simple rules that will simplify the DAG. And the simpler the DAG, the more efficient the model will be. Also, by performing some shaving, we will be able to detect more structure that we may be able to exploit later. So for instance, this rule may remove some equal parameters. So if we have something like A equals B, we just merge them together into one unique state. We also remove some constants that may happen in the cipher, and these constants are not useful for step 1. And we also remove some free parameters that we can guarantee that won't have any impact on the rest of the process. Okay, so now let's discuss our third contribution, which is constraint generation. So when we do some kind of abstraction, we want to merge some states together. And to do that, we have to be a bit clever on how we do that. One way to make that automatic is to do the following. So let's consider an operator, for instance, the XOR. It will have two inputs, each of domain 0 to 255, and will produce an output of 255. If we enumerate every possible input of the XOR, for instance, 0, 0, 1, 2, and so on, we can compute it just by doing the XOR. So 0 XOR 0 equals 0, 1 XOR 2 equals 3, 255 XOR 255 equals 0. Each of these entries will give you a feasible tuple. And if we perform some abstraction, so if it's 0, we keep it 0, and if it's something else that's 0, we just put a 1 in it. And we obtain at the end a list of valid tuples. And if we list all these valid tuples, we obtain these 5 ones, and there's 3 that won't appear. And by doing this procedure, we are making sure that every tuple we consider exists at least once in the possibilities. And each tuple that is in red here won't happen, and that we are sure of. And if we add some constraints, some table constraints like that, we are able to reach the same abstraction as the constraints people usually use in such models. Okay, so now let's discuss our final contribution. So with what I presented just before, we are able to generate step 1 models that are totally valid and that are able to provide some good solutions and some good abstractions. But there's still a problem because some people recently noticed that such model can be improved by adding new kind of constraints. So let's see why. So I have in this example some states with some operators. So for instance, A, B, D will have values 1, 1, and 1. So these values are valid regarding to this XOR operator. If we look at this one, B, C, E, which has values 1, 0, and 1, this is also valid regarding this XOR operator. And if we look at this one, we have 1, 1, 0, which is also a valid tuple. So each of these are valid locally. But if we do some math and generate some kind of new XOR constraint, in this case A, C, and F, what we'll notice is that we have the tuple 1, 0, 0, which is invalid. And this is a big problem, because it means that if we have some kind of pattern like that in our step 1 solution, we know already that it won't be valid in step 2. And we may spend a lot of time enumerating this kind of false alarms. So what we do in this work is to generate new kind of XORs similar to this, and this would allow us to have some good compromise in terms of solving time and abstraction trade-off time. Obviously, there's a lot of constraints like that, and we want to be a bit clever in the generation of such constraints. So in this paper, we use some kind of simple heuristics to optimize this kind of trade-off. So now let's discuss about the results. So for this paper, we considered 4 ciphers, which are well known, so Midori, AES, Craft, and Skinny. For each of these, we considered 2 types of attacks, single key and related key attacks. And for each of these combinations, we studied 2 kinds of problems. The step 1 opt, which is an optimization problem. We want to find the best solution, minimizing the number of active S boxes. And we want to solve the step 1 enum, which is an enumeration problem. We want to find all the optimal solutions as fast as possible. So in total, we have 16 benchmarks and 254 instances. And each of these are available in our repository if you want to test your solver. So let's discuss about performance measures. So we consider 2 criteria. First, the quality, which is the model tightness. For each of the instances, we are registering the number of solutions we believe are valid in step 1, but are not valid in step 2. And what we noticed is that we get the same quality compared to the state-of-the-art models. Also, we tried to study the efficiency, so how fast the solvers can solve our models. So we used the CPU time for 3 solvers, which are Picasa, Schuft, and Gurobi. And for each of them, we get very similar results compared to the state-of-the-art. So we are able to generate automatically some models that are competitive with the state-of-the-art human-generated models. So let's wrap up this presentation. In this presentation, we studied some way to generate automatically some mini-zinc models and compare them to the state-of-the-art. We evaluated our models on 4 ciphers, 2 attacks, and 2 problems. Also, what we could do to go a bit further is to add new kind of ciphers, more attacks. So for instance, we can add, the boomerang attack. We can integrate also the step 2. So far we only studied the abstraction, but we could make the whole chain to have a better view. And we could also study some dynamic programming algorithms that could be very efficient compared to MIPS, CP, or SAT. With that, I'm going to wrap up. I hope this presentation was interesting, and I'd be glad to answer your questions.